We stand on the edge of a new cosmic dawn. For the first time in generations, humanity is not just dreaming of the stars, but actively building the machines to touch them. This is not about a single launch or a fleeting moment of exploration. We are witnessing the simultaneous birth of 25 separate space missions, each one a blueprint for a different future. By the end of this journey, you will have a complete map of the next era of human discovery, understanding exactly how these projects will reshape our world and our species. We will send drones to alien seas, telescopes to find second Earths, and construct outposts on distant worlds. What will we become when we finally step into this vast frontier? The first cornerstone in this new era is already being laid, not on some distant world, but on our closest celestial neighbor. NASA's Artemis program marks a fundamental shift in our approach to space. This is not a repeat of Apollo, a series of brief flags and footprints. Artemis is the beginning of a permanent human presence beyond Earth. It is a meticulously planned, multi-stage campaign to build a sustainable outpost on the Moon. The journey began with Artemis 1, a monumental uncrewed test flight. In late 2022, the colossal Space Launch System rocket, the most powerful ever built, sent an Orion spacecraft on a journey around the Moon and back. This was a stress test of the entire system, proving the rocket, the capsule, and its heat shield could survive the harsh environment of deep space and the searing heat of re-entry. It was a resounding success, a green light for the next breathtaking step. That step is Artemis 2, scheduled for no earlier than September 2025. This will be the first crewed mission to the Moon in over 50 years. 4 astronauts will climb aboard Orion, not to land, but to embark on a historic flight. They will slingshot around the Moon, venturing farther from Earth than any human has ever traveled, gazing upon the lunar far side with their own eyes before returning home. This mission is about relearning how to operate in deep space, a crucial dress rehearsal for what comes next. And what comes next is the moment the world will hold its breath. Artemis 3, this is the landing mission. Its target is not the familiar, sun-baked plains of the Apollo era. Artemis 3 is headed for the lunar South Pole, a region of profound mystery and incredible promise. Here, in the permanent shadows of deep craters, scientists believe vast reservoirs of water ice lie frozen for billions of years. This water is the key to everything. It can be split into breathable oxygen and rocket fuel, turning the Moon from a destination into a gas station for the solar system. The landing will be a feat of precision, using a new human landing system to deliver the first woman and the next man to this unexplored frontier. But the vision extends far beyond a single landing. Artemis is about building to stay. Central to this plan is the Lunar Gateway, a small space station that will orbit the Moon. Think of it as a celestial base camp. Astronauts will transfer from Orion to the Gateway, then descend to the surface in their lander. The Gateway will serve as a science lab, a communications hub, and a staging point for missions to more distant regions of the lunar surface. It is also a powerful symbol of international partnership, with modules and contributions from space agencies across Europe, Japan, Canada, and others. This collective effort is not just for lunar science. Every technology tested, every lesson learned in the harsh, airless environment of the Moon is a direct rehearsal for the ultimate goal, Mars. Artemis is the proving ground, the necessary first chapter in the story of humanity becoming a multi-planetary species. It begins with a return, but its true purpose is to launch us toward a future we have only ever dreamed of. The Lunar Gateway transforms a distant celestial body into a place we can call a workplace. This small, modular space station will be humanity's first permanent outpost in orbit around another world. Unlike the massive International Space Station, the Gateway is designed for efficiency and specific purpose. It will consist of several key modules, each with a critical role. A habitation and logistics outpost provided by NASA will serve as the primary living quarters for visiting crews, complete with life support systems and storage. The European Space Agency is contributing a module for refueling, power, and communications, acting as the station's vital heart. Perhaps most intriguing is the contribution from the Canadian Space Agency, a sophisticated robotic arm system. This technology will be essential for maintaining the gateway, capturing visiting spacecraft, and even assisting astronauts during spacewalks. This international collaboration is not just symbolic, it is a practical necessity, pooling resources and expertise to build something no single nation could achieve alone. But what is the gateway actually for? Its primary function is as a staging point, a celestial base camp. Imagine astronauts launching from Earth in an Orion capsule. They would dock at the gateway, acclimatized to the deep space environment, and then transfer into a specialized human landing system for their descent to the lunar surface. Upon returning from the Moon, they would board their lander, ascend back to the gateway, prepare for the journey home, and finally board Orion for the return to Earth. This architecture makes lunar operations far more flexible and sustainable than the direct approach used during Apollo. The gateway also unlocks profound scientific potential. Its unique orbit will offer unparalleled views of both the lunar surface and deep space, free from the interference of Earth's atmosphere and magnetic field. It will host experiments on the long-term effects of deep space radiation on living organisms and materials, knowledge absolutely critical before we send humans on the years-long journey to Mars. Yet the true revolution happens not in orbit but on the ground below. The lunar South Pole, the target for Artemis landings, holds a treasure locked in eternal shadow, water ice. This discovery changes everything. Water is not just for drinking, it is a resource we can break apart. Using solar power, we can electrolyze it into hydrogen and oxygen. Oxygen is for breathing. Hydrogen and oxygen together form a powerful rocket propellant. This means future missions could, in principle, mine lunar ice and manufacture their own fuel right on the Moon. The implications are staggering. The Moon ceases to be a mere destination and becomes a gas station, a supply depot for voyages deeper into the solar system. This is the core concept of in situ resource utilization, and mastering it on the Moon is a non-negotiable rehearsal. The challenges of extracting water in a vacuum, under extreme temperature swings, and with limited infrastructure will teach us the engineering and operational principles we need to survive on Mars, where we hope to use the planet's own resources. Every robot that traverses a lunar crater, every experiment that processes regolith into oxygen, every module we add to the gateway is a step toward a future where humanity is no longer confined to a single, fragile world. The Moon is our testbed, our training ground, and our springboard. While the Moon becomes our training ground, a far more audacious treasure hunt is already underway on another world. The Mars Sample Return Campaign is arguably the most complex robotic space mission ever conceived. A celestial relay race spanning 3 separate spacecraft and an entire decade. Its prize is simple yet priceless, pristine pieces of another planet, sealed in a capsule and delivered to laboratories here on Earth. This is not a single launch but a meticulously choreographed ballet of technology, beginning with a star performer already on the Martian stage, the Perseverance rover. Since its landing in Jezero crater in 2021, Perseverance has been more than a geologist, it has been a cosmic archivist. Its core mission is to seek signs of ancient microbial life in the rocks of a dried-up river delta, where water once flowed billions of years ago. Using a sophisticated drill on its robotic arm, the rover has been collecting core samples, slender cylinders of rock and soil about the size of a piece of classroom chalk. But it does not analyze these samples itself. Instead, it carefully seals each one inside a sterilized titanium tube, creating a pristine time capsule from Mars's distant past. Perseverance has been depositing groups of these sealed tubes at a designated depot on the surface, creating a cache of scientific treasure waiting for pickup. This is where the second act of this grand drama begins. NASA and the European Space Agency plan to send a sample retrieval lander to a precise location near Jezero crater. This stationary platform will be a marvel of automation. From its deck, a small fetch rover built by the European Space Agency will roll down a ramp. This rover's sole purpose is to navigate to the sample depot, gather the tube's Perseverance left behind, and bring them back to the lander. It is a robotic courier on the most important delivery run in history. Once the samples are secured, the mission enters its most critical and never-before-attempted phase, a launch from the surface of another planet. Attached to the lander is the Mars Ascent Vehicle, a small, two-stage rocket. The fetch rover will load the sample tubes into a special container about the size of a basketball, which will then be placed into the ascent vehicle's payload bay. On a command from Earth, this rocket will ignite, blasting off from the red dust of Mars, fighting through its thin atmosphere to achieve orbit. It will be the first human-made object to ever launch from another world. But the journey is only half over. Waiting in Martian orbit will be the third spacecraft, the Earth Return Orbiter, also provided by the European Space Agency. This sophisticated satellite must locate the basketball-sized sample container as it drifts through space, rendezvous with it, and capture it using a complex mechanism, all without human guidance. Once secured, the orbiter will seal the container inside a robust, biosecure entry capsule, essentially a nested set of protective shells designed to survive an apocalyptic re-entry into Earth's atmosphere. Finally, the orbiter will fire its engines to break orbit and begin the long cruise back to our planet. Upon approach, it will release the entry capsule on a precise trajectory, sending it screaming toward a predetermined landing site, likely a remote military testing range. The capsule will slam into the ground, where a team will recover it and immediately transport its priceless contents to a state-of-the-art biocontainment facility. There, under the most stringent sterile conditions, scientists will finally open these time capsules. The scientific potential is beyond measure. In Earth-based labs, we can apply analytical tools far too large and complex to ever send to Mars. We can slice the rock into layers thinner than a human hair, peer at them with electron microscopes, and analyze their chemistry with exquisite precision. The goal is to search for biosignatures, chemical or structural patterns that could only have been produced by past life. Did Mars, when it was warm and wet, ever spark with biology? These samples could hold the definitive answer. Beyond the search for life, they will tell us the detailed geological history of Mars, revealing how its climate changed from a world of rivers to a frozen desert. They will help us understand the planet's interior and its potential to support future human explorers. This multi-billion-dollar, multi-agency endeavor is a gamble of epic proportions, but the reward is a piece of another world in our hands, a direct physical connection that could forever alter our understanding of life's place in the cosmos. The quest for life does not end with the red sands of Mars. It pushes outward toward a distant giant and its hidden, watery worlds. While we plan to bring pieces of Mars home, the European Space Agency has already launched a robotic emissary on an 8-year journey to a far more alien ocean. Its name is JUICE, the Jupiter Icy Moons Explorer, and its target is not the gas giant itself, but its 3 fascinating ice-cloaked satellites, Ganymede, Callisto, and Europa. These are not dead rocks, but full-fledged planetary worlds, each suspected to harbor vast, global oceans beneath their frozen crusts. JUICE is designed to be the ultimate investigator, armed with a suite of 10 sophisticated instruments to peer through the ice and ask one profound question: could life exist in the perpetual darkness of a world orbiting Jupiter? The mission represents a monumental engineering challenge. Launched in April 2023, the spacecraft must navigate the inner solar system, using gravity assists from Earth and Venus to build up enough speed for the long cruise to the outer system. It will arrive at Jupiter in July 2031, where it will begin a complex 3.5-year tour. Its instruments are like a scientist's perfect toolkit. Powerful cameras will map the Moon's surfaces in unprecedented detail, looking for cracks, ridges, and strange terrain that hint at geologic activity below. An ice-penetrating radar will do what its name suggests, send pulses of energy down through the icy shells to measure their thickness and maybe even glimpse the liquid interface of the hidden seas. A magnetometer will study the Moon's magnetic fields, which are induced by Jupiter's own colossal magnetism sloshing their salty, conductive oceans. Spectrometers will analyze the faint, tenuous atmospheres and surface compositions, searching for organic molecules, the chemical building blocks of life. Each moon presents a unique mystery. Callisto, the most heavily cratered, is a fossil world, its ancient surface a record of the solar system's violent early days. Europa, with its young, cracked ice shell, is believed to have the most active ocean, possibly in direct contact with a rocky seafloor where hydrothermal vents could provide energy and chemistry for life, much like they do in Earth's deepest oceans. But the crown jewel of the mission is Ganymede, the largest moon in the solar system, even bigger than the planet Mercury. Ganymede is the only moon known to generate its own intrinsic magnetic field, a clue to a complex, layered interior with a liquid iron core. The grand finale of the JUICE mission is a feat of celestial piloting never before attempted. After its tour of the Jovian system, the spacecraft will change its orbit one last time, not to return home but to be captured by Ganymede's gravity. In December 2034, JUICE will become the first human-made object to orbit a moon other than our own. From this unique vantage point, it will study Ganymede's ocean, ice shell, and magnetic field in exquisite detail, transforming it from a fuzzy point of light into a fully characterized world. The data JUICE sends back will redefine our understanding of habitable zones. Life as we know it requires liquid water, energy, and the right chemistry. We once thought only planets within a star's so-called Goldilocks zone could meet those conditions, but the Galilean moons teach us that tidal forces, the gravitational stretching from their dance with massive Jupiter, can provide the heat to keep oceans liquid far from the sun's warmth. They are proof that habitable environments can exist in the most unexpected places, locked inside frozen shells around gas giants. By characterizing these alien oceans, JUICE is not just exploring moons, it is testing the very principles of where life could arise in our cosmos and perhaps where we should look next. But Jupiter's secrets are too vast for a single explorer. As JUICE begins its long cruise, NASA is preparing its own dedicated mission to the most promising ocean world of all. The Europa Clipper is not an orbiter in the traditional sense. It is a soaring, swooping scout designed for one purpose: to determine if the hidden ocean of Europa could harbor conditions suitable for life. This moon, with its young, cracked surface resembling a fractured eggshell, has captivated scientists for decades. Beneath an ice shell perhaps only 10 to 15 miles thick sloshes a global saltwater ocean containing more than twice the volume of all Earth's oceans combined. The Clipper, scheduled to launch in October 2024, will take a different path than JUICE, using a Mars gravity assist to arrive at Jupiter in 2030. Its strategy is one of repeated, daring reconnaissance. Instead of orbiting Europa directly, which would expose it to the intense radiation of Jupiter's magnetic field, the spacecraft will enter a wide orbit around Jupiter itself. From this vantage point, it will perform nearly 50 close flybys of Europa over several years, each pass revealing a new piece of the puzzle. With each flyby, its suite of 9 instruments will gather a torrent of data. High-resolution cameras will map nearly the entire surface, scrutinizing the bizarre chaos terrain and searching for fresh signs of geologic activity. An ice-penetrating radar will measure the thickness of the icy shell and look for pockets of subsurface water, acting like a sonar for a frozen world. A thermal instrument will scan for warm spots where the ocean might be melting the ice from below, hinting at recent eruptions. Perhaps the most thrilling possibility is the hunt for plumes. The Hubble Space Telescope has provided tantalizing hints that Europa occasionally erupts, shooting geysers of water vapor from cracks in its ice into space. The Clipper is built to catch these eruptions in the act. Its instruments will be able to fly directly through any plume, analyzing the composition of the ejected material. If it can sample that spray, it will be sampling the ocean itself without ever needing to drill through miles of ice. The spacecraft spectrometers will dissect the faint light reflected from Europa's surface, identifying minerals and organic compounds. Finding complex carbon-based molecules on the surface, potentially delivered from the ocean below, would be a revolutionary discovery. Every measurement feeds into the core question of habitability. Does Europa's ocean have the right chemistry? Does it have sources of chemical energy? And is it in contact with a rocky seafloor where life-sustaining reactions could occur? The Europa Clipper is the ultimate detective, tasked with gathering enough evidence to justify the next, even more audacious step, a lander. NASA is already studying concepts for a Europa lander mission that would follow the Clipper, touching down on the icy surface, possibly near a fresh crack or plume deposit, to search for definitive biosignatures. The Clipper's maps will choose the landing site. Its data will tell us if the gamble is worth taking. So while JUICE gives us a grand tour of Jupiter's oceanic moons, the Clipper focuses a magnifying glass on the one that whispers most urgently of a hidden, living world. Yet the search for life's ingredients pushes us to an even stranger, colder laboratory. While Europa and its siblings hide their oceans under ice, one world in the Saturn system wears its organic chemistry on the surface for all to see. Titan is a place of profound paradox, a frozen moon that behaves like a twisted mirror of Earth. It is the only moon in our solar system with a substantial atmosphere, a thick, hazy orange shroud of nitrogen and methane that is denser than the air we breathe. Beneath that smog, the landscape is both eerily familiar and utterly alien. Titan has rain that carves river valleys, it has great lakes and seas that ebb and flow with tides, and it has vast dunes sculpted by wind. But the rain is liquid methane, falling at nearly 300 degrees below zero. The lakes are not water, but pools of ethane and methane, forming the only known stable liquid bodies on any world besides Earth. And the dunes are not sand, but grains of frozen hydrocarbon, organic compounds that are the building blocks of life as we know it. This is a world where the chemistry of life is happening everywhere, frozen in a perpetual prebiotic state. To explore this bizarre organic factory, NASA is building not a rover but a flying laboratory. The Dragonfly mission is a revolutionary concept, a nuclear-powered rotorcraft the size of a small car. Imagine a large drone equipped with 8 rotors designed to fly through Titan's thick, calm atmosphere, which makes flight far easier than on Earth. Dragonfly will be an explorer of unprecedented mobility. It will launch in 2027 and arrive at Titan in the mid-2030s, descending by parachute through the orange haze. Its first landing site is targeted for the Shangri-La Dune Fields, a region of dark, organic sand. But Dragonfly will not stay put. Over a planned mission of nearly 3 years, this rotorcraft will embark on a series of daring flights, traveling tens of miles at a time to sample and study radically different environments. It might land on the icy shores of a methane lake, then fly to the floor of an ancient impact crater where liquid water may have once mixed with organic molecules. At each stop, it will become a stationary science station. Its instruments will drill into the icy surface to collect samples, then analyze them in an onboard laboratory called a mass spectrometer. This will allow scientists to identify the complex organic compounds present, essentially taking an inventory of Titan's chemical stockpile. The mission's core goal is to study prebiotic chemistry, the steps that occur before life emerges. Titan is a natural laboratory for this process, cold and devoid of liquid water, but churning with the same carbon-rich molecules that likely seeded our own planet. By seeing how far chemistry can progress in this environment, we learn what is necessary and what is merely possible for life to begin. In a profound way, Titan may offer a glimpse of a frozen, alternate timeline for Earth, showing us what our own planet might have been like before life rewrote the rules. Dragonfly is not searching for life itself, but for the pathways that lead to it, charting the chemical map of a world where the recipe for existence is written across every dune and every raindrop. Titan's frozen chemistry offers a window into life's raw ingredients, but to find a world where those ingredients have already sparked, we must look to the stars themselves. Our search for a true second Earth has just gained its most powerful tool. The James Webb Space Telescope is not a new mission in the traditional sense. It is already floating 1 million miles away, its golden mirror open to the cosmos. But its true story is only beginning to unfold. This is not a machine designed for a single discovery. It is an ongoing revolution, a new set of eyes that will spend the coming decade rewriting the textbooks of our universe. Its extended mission promises to answer questions we have only dared to whisper, from the cradle of the first galaxies to the atmospheres of distant, potentially living worlds. At the heart of this quest is a capability that feels like science fiction made real. Webb is an atmospheric detective for planets orbiting other stars. When an exoplanet passes in front of its host star, a tiny fraction of the star's light filters through the planet's thin envelope of gases. Webb's exquisite infrared instruments can dissect that faint starlight, separating it into a spectrum, a chemical barcode. Each molecule in the atmosphere absorbs light at unique fingerprints. From a distance of hundreds of light years, Webb can read that barcode and tell us what that alien air is made of. The hunt is for combinations of gases that should not exist together without a continuous source, a biosignature. On Earth, the abundant oxygen in our atmosphere is maintained by life, by plants and photosynthesis. Finding both oxygen and methane, which normally destroy each other, in an exoplanet's atmosphere would be a tantalizing hint of biological activity. Webb is already performing these observations on planets like K218b, a promising world in its star's habitable zone, and its findings in the years ahead will transform exoplanet science from simple cataloging to profound chemical interrogation. But Webb's gaze also pierces the deepest past. By staring for days at a single, seemingly empty patch of sky, it gathers the faintest photons that have traveled for over 13 billion years. It is looking back to a time when the first galaxies were assembling out of the primordial darkness, just a few 100 million years after the Big Bang. These infant galaxies are not the majestic spirals we see today. They are small, chaotic, and furiously birthing stars. Webb's images have already shattered records, revealing galaxies earlier in cosmic history than any model predicted, forcing astronomers to reconsider how structure formed in the early universe. Every new deep field image is a time capsule, a direct snapshot of cosmic childhood. Closer to home, within our own Milky Way, Webb acts as an infrared spotlight cutting through cosmic dust. Thick clouds of dust and gas that are opaque to visible light become transparent to Webb's vision. This allows it to peer directly into the stellar nurseries where stars and planets are being born. We can watch in unprecedented detail as a collapsing cloud of gas forms a protostar, and see the swirling disks of material around young stars where planets are coalescing. Within those disks, Webb can identify the chemical signatures of water, organic molecules, and the raw materials for future worlds, tracing the path from simple chemistry to potential habitability. The telescope's extended mission means it will continue this work for years, possibly decades. Each observation builds upon the last, creating a cumulative legacy of discovery. It will survey thousands of exoplanet atmospheres, building a statistical understanding of what is common and what is rare. It will push the cosmic frontier back ever closer to the dawn of time. And it will chronicle the intimate process of planetary birth across our galaxy. The James Webb Space Telescope is not just a tool for answering old questions, it is an engine for generating new ones, ensuring that our map of reality is redrawn with every new image it beams back to a waiting Earth. While Webb stares deep into cosmic history with its piercing gaze, another telescope will soon take in the entire sky with a sweeping view. NASA's Nancy Grace Roman Space Telescope, named for the pioneering astronomer who paved the way for Hubble, is built for a different kind of revelation. If Webb is a powerful microscope examining individual cells of the universe, Roman will be the wide-angle lens capturing the entire organism. Its primary mission is to conduct vast panoramic surveys of the cosmos, addressing two of the greatest mysteries in modern physics: dark energy and dark matter, while simultaneously performing a galactic census of planets on an unimaginable scale. At the heart of the telescope is a camera with a field of view over 100 times larger than Hubble's infrared instrument. This allows it to observe enormous swaths of sky quickly and efficiently. In just its first 5 years of operation, Roman is expected to measure light from over 1 billion galaxies and survey the plane of our Milky Way hundreds of times. This colossal dataset is the key to mapping the large-scale structure of the universe with unprecedented precision. Scientists will use it to trace how the distribution of galaxies has changed over cosmic time. The driving force behind that expansion, the mysterious anti-gravity we call dark energy, leaves its fingerprint in this structure. By measuring how the clustering of galaxies has evolved across billions of years, Roman will test whether dark energy has remained constant or changed over the life of the universe, helping us understand the ultimate fate of all things. But Roman's vision extends beyond the light we can see. It will also map the dark matter scaffolding that holds galaxies together. Dark matter does not emit light, but its immense gravity bends the path of light from distant galaxies, a phenomenon called weak gravitational lensing. Roman will measure the subtle distortions in the shapes of millions of those background galaxies, allowing astronomers to create a three-dimensional map of the invisible dark matter that permeates space. Yet for all its grand cosmological ambitions, one of Roman's most thrilling capabilities brings the search for other worlds into stunning focus. The telescope will perform a massive microlensing survey. Here is how this cosmic magic trick works. When a massive object like a star or even a planet passes in front of a more distant star, its gravity acts as a lens, magnifying and brightening the background star's light for a short period. If the foreground object has a planet orbiting it, that planet creates its own tiny spike in the light curve. This method is uniquely powerful because it can find planets incredibly far away across the galaxy, and it is especially sensitive to planets orbiting at great distances from their stars, similar to our solar system's gas giants. Most remarkably, microlensing can detect planets that have no sun at all, worlds flung from their star systems to drift alone through the interstellar darkness. Roman's survey is predicted to discover thousands of new exoplanets, effectively taking a demographic survey of our galaxy's planetary population. For the first time, we will get a statistically meaningful answer to how common Earth-like planets are in the habitable zones of their stars. We will learn the typical distance planets orbit, and perhaps most hauntingly, we will begin to count the number of rogue, free-floating worlds that wander the galaxy untethered. Are these dark, frozen orphans more common than stars themselves? Roman is designed to find out. By connecting the immense architecture of the cosmos with the intimate discovery of distant worlds, the Nancy Grace Roman Space Telescope will weave together the story of everything, from the invisible forces shaping the universe to the countless islands that may harbor life within it. The quest for a second Earth demands a census of unprecedented precision. While Roman will map the galaxy's planetary population from afar, a new European mission is being built to find the specific targets we most desire, rocky worlds orbiting stars like our own Sun. This is PLATO, the Planetary Transits and Oscillations of Stars mission, a spacecraft engineered not just to find planets, but to understand the very stars they call home. Its genius lies in a deceptively simple method with profound implications. PLATO will stare at hundreds of thousands of bright stars, watching for the telltale, rhythmic dimming that occurs when a planet passes in front of its star. This transit method is not new, but PLATO's execution is revolutionary. The spacecraft will carry not one or two telescopes, but an array of 26 separate cameras, all pointing at adjacent patches of sky. This multi-eyed design allows it to monitor a vast field of stars with incredible stability and sensitivity. It can detect dips in starlight so minuscule they are caused by planets only slightly larger than Earth. But PLATO goes far beyond mere detection. Its second name, Oscillations of Stars, reveals its deeper power. Stars are not silent, static orbs. They pulsate and vibrate like colossal musical instruments. These subtle brightness oscillations, caused by sound waves trapped inside the stellar interior, are a form of stellar seismology. By analyzing these stellar quakes, PLATO can measure a star's properties with extraordinary accuracy. We can learn its exact size, its mass, its internal structure, and most importantly, its age. This is the mission's masterstroke. For the first time, we will not just find an Earth-sized planet in the habitable zone, we will know the precise age of its sun. Is that star a turbulent, youthful 5 billion year old, similar to our Sun, or a quiet elder 10 billion years old? This changes everything. A planet's history, its climate, and its chance to develop life are intimately tied to the life story of its star. By pairing an exoplanet's size with the known mass and radius of its star, scientists can calculate the planet's density, telling us if it is a gassy mini-Neptune or a dense, rocky world like our own. PLATO's ultimate goal is to build a definitive catalogue of these worlds. It aims to discover and characterize thousands of new planetary systems, but its treasure will be the dozens of truly Earth-like candidates it finds orbiting Sun-like stars. These will not be vague possibilities, but well-characterized targets. We will know their orbital periods, their sizes, their likely compositions, and the nature of the stars they orbit. This catalogue will provide the essential shortlist for the next generation of telescopes, like the future extremely large telescopes on the ground, which will attempt to take direct images and analyze the atmospheres of these specific worlds. PLATO is the meticulous surveyor, drawing the most detailed map yet of our stellar neighborhood, and marking with a bright red circle the doors we most need to knock on next. Venus stands as a stark, terrifying warning. While we search for Earth-like worlds across the galaxy, our closest planetary neighbor shows us a vision of apocalypse made real. Its surface is hot enough to melt lead, crushed under an atmosphere 90 times thicker than Earth's, shrouded in clouds of sulfuric acid. This is not a world that invites visitors, yet NASA is preparing to send a probe on a one-way dive into the inferno. The DAVINCI mission, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, is a bold act of planetary interrogation. Its goal is not to land but to descend, to use its final hour of existence to unravel the deepest secrets of how a world so similar to ours became so utterly alien. The mission centers on a single, heroic instrument package, a spherical descent probe about 3 feet across, built like a titanium diving bell. It will be carried to Venus by a spacecraft that will first map the planet's clouds, but the true drama begins when this sphere is released. Plunging into the upper atmosphere, it will begin a harrowing, hour-long free fall. A parachute will deploy briefly to stabilize its initial descent, but then it will be jettisoned, allowing the probe to sink rapidly through the thick, soupy air. This is by design. A slow descent would let the probe overheat before it could reach the lower atmosphere where the most crucial measurements must be taken. So it will fall like a stone, enduring immense pressure and scorching heat, all while its suite of 5 instruments frantically samples the air. Its sensors will act like a chemical bloodhound, sniffing the atmosphere layer by layer. They will measure the precise ratios of noble gases like argon and xenon. These inert gases are cosmic time capsules, unaffected by chemical reactions, holding clues to how and when Venus's atmosphere originally formed and whether it ever shared a similar history with Earth. Other instruments will analyze the composition of the sulfuric acid clouds and trace the amounts of water vapor and sulfur compounds at different altitudes. But perhaps the most breathtaking moment will come in the final minutes of the descent. As the probe nears the surface, a hardened window on its side will allow a camera system to activate. For the first time, we will get high-resolution, visible light images of a vast, rugged highland region called Alpha Regio. We will not see a global panorama, but a dynamic, close-up view of the terrain as the probe descends, looking for signs of ancient rock types and tectonic deformation. These will be the first images of the Venusian surface since the Soviet Venera landers in the 1980s, and with modern technology, they will be infinitely clearer. Every bit of this data streams back to the carrier spacecraft overhead until the very moment the probe is crushed and melted. The sacrifice is for answers to profound questions. A primary target is Venus's runaway greenhouse effect. We understand the basics. Sunlight heats the surface, but the thick carbon dioxide atmosphere traps that heat relentlessly. Yet the devil is in the details. DAVINCI+ will measure how much heat is escaping at different levels, identifying the specific gases and processes that make the trap so efficient. This is not just about Venus, it is a masterclass in climate physics, a dire case study for our own planet. Another haunting question is whether Venus was ever habitable. Some models suggest it may have had a shallow, global ocean for billions of years before its greenhouse effect spiraled out of control. DAVINCI will search for a telltale sign in the atmosphere, a specific ratio of deuterium to normal hydrogen. On Earth, a high ratio of this heavy hydrogen in our oceans indicates that over time, regular hydrogen escaped to space. If Venus shows an even more extreme ratio, it could be the ghostly fingerprint of a vast, long-vanished sea. Finally, the mission will investigate the bizarre chemical cycles that maintain the planet's hellish equilibrium. The sulfuric acid clouds should rain out and remove sulfur from the atmosphere over time, yet they persist. Something, perhaps volcanic activity, is continuously replenishing them. By mapping the chemistry in detail, DAVINCI may catch this cycle in action, revealing if Venus is a dead world or a geologically simmering one. This single, daring plunge is a mission to diagnose a planetary catastrophe, to read the history of a lost world in the chemistry of its scorching winds, and to understand the fine line between a garden and a furnace. While DAVINCI+ takes a deep, sacrificial plunge into the atmosphere, another mission will settle into orbit to study the entire planet with a scientist's patient, comprehensive gaze. The European Space Agency's EnVision orbiter is designed to be the ultimate planetary physician, performing a complete scan of Venus from its churning clouds down to its hidden mantle. This is not a fleeting flyby, but a dedicated, multi-year survey mission to diagnose how Earth's twin became its terrifying opposite. EnVision will carry a powerful suite of instruments that work in concert, each answering a different piece of the planetary puzzle. A synthetic aperture radar will pierce the perpetual cloud cover to map the surface in resolution comparable to the best images we have of Mars. It will chart volcanoes, vast lava plains, and bizarre tectonic features called tesserae, which may be the remains of ancient continents. This radar will not just look at the surface, it will see beneath it. By analyzing the radar signals that penetrate the ground, scientists hope to detect layers of different rock types and even find evidence of buried lava flows or impact craters, creating the first geological map of Venus's subsurface. Complementing the radar, a suite of spectrometers will analyze the faint light reflected from the surface and the atmosphere. Different minerals absorb light in unique ways, so these instruments can identify the rock compositions of those surface features from orbit. Are the tesserae made of granite-like rocks, which on Earth require water to form? This single finding could revolutionize our understanding of Venus's ancient past. Other spectrometers will act as atmospheric detectives, tracing the presence of minute amounts of sulfur dioxide, water vapor, and other gases. They will monitor how these gases vary across the planet and over time, searching for clues of ongoing volcanic activity. The plumes from erupting volcanoes would inject gases into the atmosphere, and EnVision is designed to catch them in the act, answering the long-standing question of whether Venus is volcanically dead or merely dormant. A third powerful tool is a radio science experiment. By precisely tracking the subtle changes in EnVision's orbit caused by Venus's gravity, scientists can map the planet's gravitational field in exquisite detail. Variations in gravity reveal the density of the rock below, showing where massive mountain ranges have deep roots or where hot, buoyant plumes are rising from the mantle. This allows EnVision to virtually peer hundreds of miles down, charting the structure of the planet's interior and its current geologic activity. The core mission of EnVision is to connect these disparate threads into one coherent story. It seeks to understand the relationship between the interior engine of the planet and its surface and atmospheric evolution. On Earth, plate tectonics acts as a global thermostat, recycling carbon dioxide into the mantle over millions of years. Venus shows no evidence of such a process. Did it ever have plate tectonics that shut down? Is its carbon dioxide all trapped in the atmosphere because its interior stopped recycling it? By linking volcanic and tectonic activity seen on the surface with measurements of current atmospheric gases and internal heat flow, EnVision will reconstruct Venus's geological history. It will tell us if the planet experienced a catastrophic resurfacing event 500 million years ago, or if its geology has been a slow, steady simmer. Most importantly, by comparing this complete planetary profile to Earth's, we learn what factors are essential for maintaining a habitable climate over billions of years. EnVision and DAVINci are a perfect partnership, one providing deep, localized chemical truths, the other delivering a global, interconnected context. Together, they will transform Venus from a symbol of hellish mystery into an understood case study, a stark lesson in planetary destiny written across the face of our nearest neighbor. Our view of the cosmos is about to shift from a series of still photographs to a breathtaking, high-definition film, perched atop a mountain in Chile, the Vera Sea. Rubin Observatory is preparing to conduct a 10-year experiment of staggering ambition, the Legacy Survey of Space and Time. This is not a telescope built to stare at one object, but to watch everything all at once. Its primary instrument is a digital camera the size of a small car, with a resolution of 3.2 billion pixels. Every few nights, this behemoth will capture a complete panorama of the entire visible southern sky, and then do it again and again for an entire decade. The result will be the deepest, widest astronomical movie ever made, a time-lapse of the universe on a scale we have never before attempted. The data torrent will be almost incomprehensible, requiring an entire new branch of data science to handle the tens of petabytes of images it will produce. Each nightly sweep will be compared to the last, and this is where the magic happens. The software will flag anything that has changed, moved, or appeared. This constant vigilance means the sky will never again be static. The survey will transform our understanding of our own cosmic backyard by discovering millions of new objects within our solar system. We are talking about a vast population of asteroids, particularly those that orbit between Jupiter and Neptune, and icy bodies in the distant Kuiper belt beyond Pluto. It will find countless interstellar visitors like the mysterious Oumuamua, giving us a statistical understanding of how common such vagabond rocks are. Crucially, it is predicted to find over 90% of the potentially hazardous near-Earth asteroids larger than a few hundred meters, completing a planetary defense catalog that has been generations in the making. But its gaze reaches far beyond our solar system. By repeatedly imaging the same star fields, the survey will map the structure of our Milky Way galaxy in 3 dimensions with unprecedented detail. It will trace the distribution of dark matter through the subtle warping of light from distant galaxies, a technique called weak gravitational lensing, but on a scale that dwarfs all previous efforts. Perhaps most thrilling is the observatory's destiny as a master of the cosmic transient. The universe is filled with violent, fleeting events that blink into existence and then fade away. Traditional telescopes often discover them too late. The Legacy survey will catch them as they happen. It will alert astronomers worldwide within 60 seconds of detecting a new supernova, the explosive death of a star. It will spot the brilliant mergers of neutron stars called kilonovae, which forge heavy elements like gold and platinum. It could detect the mysterious flashes from stars being shredded by black holes or the unpredictable eruptions of distant quasars. This real-time celestial alert system means that for the first time, other telescopes, like the James Webb Space Telescope, can instantly swivel to point at these events, studying them in their earliest, most critical moments. The Vera C. Rubin Observatory does not just add to our knowledge, it changes the very rhythm of discovery, turning the silent sky into a dynamic, ever-changing spectacle we are finally equipped to witness. The Vera Rubin Observatory will watch the sky change, but on the Moon, a new power is preparing to build something permanent. China's lunar ambitions represent a parallel track to Artemis, a comprehensive, step-by-step campaign to claim a leading role in humanity's return to the Moon. This is not a single mission, but a deliberate sequence of robotic explorers, each more complex than the last, all building toward an astonishing goal: a crewed lunar base established in partnership with other nations. The next steps in this plan are already on the launch manifest, beginning with a mission that will make history. Chang 6 is set to be the first spacecraft ever to return soil and rock samples from the far side of the Moon. Building on the success of Chang 5, which brought back samples from the near side in 2020, this mission will target the South Pole Aitken Basin, one of the oldest and largest impact craters in the entire solar system. Material from this region, untouched by the volcanic flows that resurfaced the near side, could contain clues to the Moon's violent early history and the heavy bombardment that shaped all the inner planets. The mission will require a relay satellite already in orbit to communicate with Earth, as the lunar far side is forever turned away from our planet, a technical hurdle China has already mastered with the Chang 4 lander. After Chang 6 collects its precious cargo and launches it back to Earth, the focus shifts squarely to the resource hunt. Chang 7 is a sophisticated South Pole surveyor, a mission comprising an orbiter, a lander, a rover, and a revolutionary hopping probe. Its instruments are designed to find water. A radar will scan beneath the surface, searching for ice deposits in shadowed craters. A mineral spectrometer will map the distribution of water molecules and hydroxyl bound in the soil. The mission may even include a small flying drone to scout terrain too rough for a rover. The goal is to create a detailed resource map of the lunar South Pole, identifying the most promising deposits for future extraction. This directly sets the stage for Chang 8, the critical technology demonstration. this mission will test in situ resource utilization, the very processes needed to live off the lunar land. Experiments could include using solar energy to melt regolith for construction materials, or attempting to extract oxygen and water from the soil and rocks. It is a trial run for turning lunar dirt into water, air, and building blocks, but these robotic missions are just the foundation for a vision far grander than any single flag planting. China, in partnership with Russia, has formally proposed the International Lunar Research Station, a project that mirrors the scope of Artemis but with a distinct collaborative framework. The plan outlines a robotic phase throughout the 2020s, where landers, rovers, and orbiting infrastructure are deployed. This would be followed by a crewed phase in the 2030s, where astronauts would begin extended stays on the surface. The stated purpose is open-ended scientific research and the testing of technologies for sustainable presence. But the unspoken reality is a new space race for lunar influence and resources. The International Lunar Research Station is actively seeking other international partners, offering an alternative vision of lunar governance and cooperation. This creates a fascinating and potentially tense dynamic. Two separate pathways, Artemis and the International Lunar Research Station, are now converging on the same strategic location, the resource-rich lunar South Pole. Will they operate as rival outposts, or will bridges eventually be built between them? The coming decade will determine whether the Moon becomes a new frontier for geopolitical competition, or the first off-world example of cautious, practical collaboration. But the Moon is not the only celestial object that demands our vigilance. A silent, ancient threat still drifts through the inner solar system, remnants of the violent birth of the planets. For decades, our efforts to find potentially hazardous asteroids have been like searching for black rocks on a dark night, relying on ground-based telescopes that can only scan the sky after sunset. This leaves a dangerous blind spot, the direction of the sun. An asteroid approaching from that glare is invisible until it is frighteningly close. To finally see these hidden dangers, NASA is building a sentinel that will operate in the one place with a perfect view, deep space. The NEO Surveyor, the Near-Earth Object Surveyor, is a specialized infrared space telescope with a single, vital purpose: planetary defense. Unlike optical telescopes, NEO Surveyor's infrared sensors detect heat, not reflected sunlight. An asteroid, even a dark, charcoal black one that absorbs most visible light, is warmed by the sun and glows in infrared. This means the spacecraft can spot objects that are virtually invisible to traditional surveys, particularly those that lurk in the sunward direction. It will be stationed at a gravitationally stable point between Earth and the Sun, constantly scanning the regions of space closest to our star's blinding glare. Its mission is born from a sobering congressional mandate to find at least 90% of all near-Earth objects larger than 140 meters, roughly the size of a football stadium. An impact from an object that size would not cause global extinction, but it could devastate an entire region, unleashing energy equivalent to thousands of nuclear weapons. By cataloging these objects decades in advance, we give ourselves the time to plan, to potentially deflect a threatening asteroid with a kinetic impactor, like the DART mission proved possible, or with other future technologies. NEO Surveyor is not just about finding rocks, it is about finding them early. Its systematic, years-long survey will map the orbits of hundreds of thousands of asteroids, calculating their trajectories centuries into the future. It will transform planetary defense from a reactive gamble into a predictable science, turning the unknown into the catalogued and giving humanity the ultimate gift, the certainty of time to protect our shared home. The catalogue of threats and treasures in our own solar system is a map of our immediate future, but the ultimate frontier lies far beyond its borders. A quiet meeting in a conference room over a decade ago sparked an idea so audacious it seemed pulled from science fiction, yet it is now a serious research endeavor backed by some of the brightest minds in physics. The Breakthrough Starshot initiative proposes a leap of imagination so vast it redefines the possible, to send a probe to another star within a single human lifetime. Its target is the Alpha Centauri system, our nearest stellar neighbor, a trio of stars just over 4 light-years away. For a conventional spacecraft like Voyager, that journey would take over 70,000 years. Starshot's goal is to do it in 20. The concept is breathtakingly simple in theory and monumentally difficult in practice. Instead of a massive ship carrying its own fuel, the mission envisions a fleet of gram-scale nanocrafts, each no larger than a postage stamp. These would be attached to a thin, reflective light sail, a sheet of material only a few atoms thick. The propulsion would not come from a rocket on board, but from a colossal array of ground-based lasers stationed on Earth. This phased array, spanning perhaps a square kilometer, would combine its beams into a single, incredibly powerful light pulse aimed at the departing sails. For a few minutes, this laser would shine with an intensity greater than 1,000,000 suns, pushing on the reflective sails with pure radiation pressure. The acceleration would be violent, hurling the tiny probes to a significant fraction of the speed of light, perhaps 20%, in a matter of minutes. Imagine a gust of light so powerful it could blow a butterfly across the galaxy. The technological hurdles are staggering. The light sail must be perfectly reflective, incredibly lightweight, and able to withstand that sudden, crushing acceleration without tearing. It must also navigate autonomously, correcting its course with minute thrusters over a 20-year voyage. The laser array itself is an engineering project without precedent, requiring advances in power generation, beam combining, and atmospheric compensation to fire through Earth's turbulent air without scattering. Then comes the greatest challenge of all, communication. After a 20-year flight, a successful nanocraft would scream past the Alpha Centauri system in a matter of hours. In that fleeting window, its tiny onboard camera must snap images of any planets, and a laser no bigger than a grain of rice must beam that data back across the trillions of miles to a waiting receiver on Earth. The signal would be incredibly faint, requiring a network of telescopes perhaps the size of entire countries to detect it. This is a mission of extreme minimalism and maximalist ambition. The payoff, however, would be a revelation that echoes through history. For the first time, we would have a direct image of an exoplanet, not a date to point on a graph or a blurry speck, but a detailed photograph of another world orbiting another sun. We could see cloud patterns, continents, oceans. We could answer the most profound question of all: is there a pale blue dot in that alien system too? Starshot is a gamble on the exponential curve of technology, a bet that the miniaturization of electronics and the advancement of photonics will continue unabated. It is not a mission for this decade or even the next, but a beacon for the century to come, proving that the stars are not an impossible destination, but a formidable engineering problem waiting to be solved. While Starshot dreams of reaching other stars, a new telescope is preparing to map the entire universe from our own cosmic doorstep. NASA's SPHEREX mission has a name that reveals its grand ambition: the spectrophotometer for the history of the universe, epoch of reionization and ICE's explorer. This is an all-sky surveyor of a different kind, designed not to take pretty pictures, but to collect millions of spectra, the chemical barcodes of light. It will scan the entire sky not once, but twice, in 96 different colors of near-infrared light, creating a three-dimensional map of the cosmos on a scale we have never before attempted. Its mission weaves together three epic stories, from the first blush of cosmic dawn to the birth of planets in our own galactic neighborhood. The first story begins just moments after the Big Bang. In the universe's infancy, space was filled with a hot, dense fog of particles. As it expanded and cooled, protons and electrons combined to form neutral hydrogen atoms, allowing light to travel freely for the first time. This is the cosmic microwave background, the oldest light we can see. But then, hundreds of millions of years later, something happened. The first stars and galaxies ignited, and their intense ultraviolet radiation began to rip apart those neutral hydrogen atoms, reionizing the universe and making it transparent to the types of light we see today. This epoch of reionization is a cosmic turning point we understand only in theory. SPHEREX will hunt for its faint signature by mapping the pattern of galaxies across immense distances. Because light takes time to travel, looking farther away means looking back in time. By measuring the precise clustering of millions of galaxies across different eras, the mission can trace how the large-scale structure of the universe evolved during this critical period of cosmic history, watching as the first great structures pulled themselves together from the primordial dark. The second story is one of cosmic construction, the life cycle of galaxies. As SPHEREX maps the sky, it will measure the light from over 300 million galaxies near and far. Its spectral data will allow scientists to calculate the redshift of each one, which tells us not only its distance, but also how fast it is moving away from us due to the expansion of space. This will let astronomers construct a three-dimensional map of the universe's large-scale structure with unprecedented completeness. They can see how galaxies are woven into the cosmic web, connected by filaments of dark matter, and identify where and when in cosmic history galaxies were most actively forming stars. It is like taking a census of cities across all of human history, from ancient villages to modern metropolises, to understand the rules of civilization itself. But the third story brings the cosmic journey home to the frozen chemistry of our own Milky Way. SPHEREX has a unique ability to detect the faint infrared fingerprints of specific ices. In the cold, dark clouds where stars and planets are born, water, carbon monoxide, and complex organic molecules freeze onto tiny dust grains, forming icy mantles. These ices are the raw material for future planets and the building blocks of life. The telescope will survey these stellar nurseries across the galaxy, creating a map of where these essential ingredients are most abundant. We will learn how common water ice is in planet-forming regions and where the complex organic molecules that might seed life are concentrated. This is a galactic inventory of life's potential, charting the distribution of the very same materials that coalesced to form our own solar system billions of years ago. By connecting the universe's first light to the frost in a stellar nursery, SPHEREX creates a bridge between cosmology and astrobiology, telling a single, continuous story of how a simple, hot universe evolved into one rich with the chemistry for worlds and perhaps for life. But to hear the deepest, most resonant notes in the cosmic symphony, we must leave the vibrations of Earth behind entirely. The universe's most powerful events do not announce themselves with light, but with ripples in the fabric of reality itself. The European Space Agency's LIS mission, the Laser Interferometer Space Antenna, is an instrument of almost impossible sensitivity, designed to listen to the whispers of spacetime. It will not be a single telescope, but a constellation of three identical spacecraft, flying in a vast triangular formation 2.5 million kilometers on each side, trailing behind Earth in its orbit around the Sun. They will be connected not by cables, but by beams of laser light. The principle is one of exquisite precision. Each spacecraft will fire a laser at the other two, creating a pair of perfect laser links along each arm of the triangle. The mission's entire purpose is to measure the length of these arms with phenomenal accuracy. When a gravitational wave, a ripple generated by a cataclysm in the distant cosmos, passes through the formation, it will ever so slightly stretch and squeeze the space between the spacecraft. One arm of the triangle will grow minutely longer while another grows shorter. This distortion, smaller than the width of a single atom over a distance of millions of kilometers, will change the travel time of the laser beams. By monitoring the interference pattern of the returning light, LISA can detect that change, translating it into a direct recording of the gravitational wave. This architecture in the quiet of space solves the fundamental limitation of ground-based detectors like LIGO. On Earth, seismic noise and other vibrations drown out the longest, lowest-frequency gravitational waves. In the serene, free fall of their solar orbit, the LISA spacecraft create an environment of unmatched stillness, allowing them to tune into a completely different part of the gravitational spectrum. This is the key to unlocking a hidden universe. LISA will hear the low, rumbling hum of events that unfold over months or years. Its prime target is the slow, spiraling dance of supermassive black holes. When galaxies collide, their central black holes, each weighing millions or billions of times the mass of our Sun, eventually sink to the center and begin orbiting one another. For eons, they circle, churning spacetime itself, emitting a gravitational wave signal that steadily rises in pitch and intensity until they finally merge in an unimaginable crash. LISA will detect these pairs from across the universe, charting their orbits and listening for the moment of collision. It could tell us how these monstrous objects grew so large and how often such cosmic mergers occur. But the mission's reach extends to even more exotic phenomena. It may detect the background hum from the very birth of the universe, a relic of cosmic inflation. It could hear the signals from thousands of binary systems within our own galaxy, pairs of white dwarfs or neutron stars steadily orbiting each other. Perhaps most intriguingly, it might capture the signal of a smaller stellar mass black hole being swallowed by a supermassive one at the heart of a distant galaxy, a process called an extreme mass ratio inspiral. This would allow scientists to map the warped spacetime around the supermassive black hole with precision, testing Einstein's theory of general relativity in its most extreme regime. By listening to the vibrations of spacetime itself, LISA does not observe the universe, it feels its heartbeat, revealing a dimension of reality forever hidden from traditional telescopes. Deep within the asteroid belt between Mars and Jupiter orbits a relic from the solar system's most violent era. The asteroid Psyche is not a typical rocky or icy body. It is a world of almost pure metal, a colossal, battered nugget of iron and nickel over 200 kilometers wide. Scientists believe it is the stripped bare, exposed core of a protoplanet, a fledgling world whose rocky outer layers were violently blasted away in the chaotic collisions of the early solar system. If true, this makes Psyche a one-of-a-kind time capsule, a direct window into the hidden heart of a planet. To reach this metallic enigma, NASA has built a spacecraft of elegant innovation, also named Psyche, which is now on its long cruise through interplanetary space. The mission's journey itself is a feat of modern engineering. Launched in October 2023, the spacecraft is not taking a direct path. It will use a gravity assist from Mars in 2026, a celestial slingshot that will bend its trajectory and fling it toward its target, with arrival scheduled for August 2029. The propulsion for this multi-year voyage is revolutionary. The Psyche spacecraft is powered by solar electric propulsion, often called ion propulsion. Here is how it works. Large solar arrays convert sunlight into electricity, which is used to ionize xenon gas, a neutral propellant. These charged ions are then accelerated out of the spacecraft's thrusters by a powerful electric field, creating a gentle but incredibly efficient thrust. The stream of blue glowing ions is so faint you could barely feel it on your hand, but in the frictionless vacuum of space, this continuous push can build up tremendous speed over time. It is like a sailboat with a steady breeze rather than a speedboat with a sudden burst, allowing the spacecraft to carry less fuel and more science. Once it arrives, the spacecraft's suite of instruments will begin an intensive investigation to confirm Psyche's true nature. A multispectral imager will take high-resolution pictures of the metallic surface, mapping its topography and searching for any remnants of silicate rock that might hint at its lost mantle. A gamma-ray and neutron spectrometer will peer deeper, measuring the asteroid's elemental composition by detecting the unique signatures given off when cosmic rays strike its surface. This will tell us the precise ratios of iron, nickel, and other metals, revealing if this truly is a core like our own Earth's. Perhaps the most crucial instrument is a magnetometer. Planetary cores are dynamos churning molten metal that generates global magnetic fields. If Psyche is a fossil core, it may still retain a remnant magnetic field frozen into its metal. Detecting that fossil magnetism would be the smoking gun, definitive proof that this asteroid was once the molten heart of a much larger world. The scientific payoff is profound. By studying Psyche, we are conducting a form of interplanetary archaeology, examining a building block that never finished its construction. We have never seen a planetary core directly. Our own Earth is locked away under thousands of miles of rock and mantle. Psyche offers a chance to understand the fundamental process of planetary differentiation, the settling of dense metals to the center while lighter rocks float outward. This process shaped every rocky planet, including our own, dictating their internal structure, magnetic fields, and ultimately, their potential to support life. The mission will also explore a world of bizarre geology. On a metal surface, impacts would behave differently, perhaps creating strange metallic spikes or ejecting molten metal droplets that solidified into iron rain. There could be vast metal cliffs and landscapes shimmering with a dull, metallic sheen, utterly alien to anything we have explored before. Psyche is more than a destination. It is a key to unlocking the hidden history written in metal, a chance to touch the exposed heart of a world that never was. The silent, battered hearts of ancient worlds are not the only relics drifting through our solar system. Orbiting the red planet are two of its most enduring mysteries, the lumpy, misshapen moons Phobos and Deimos. For decades, they have appeared as little more than faint dots in telescopes, their origins a subject of intense debate. Now, Japan's space agency, JAXA, is preparing to solve that puzzle with a mission of extraordinary ambition. The Martian Moon's E-Exploration, or MMX, is a robotic spacecraft designed not just to visit these enigmatic bodies, but to bring a piece of one home. This mission will execute a complex, multi-year dance around Mars, conducting the first detailed reconnaissance of both moons before attempting a daring touchdown on the larger one, Phobos, to retrieve a precious sample of its surface. The journey is a masterpiece of celestial navigation. After its launch, MMX will travel to Mars and enter a peculiar orbit that allows it to repeatedly swing close to both Phobos and Deimos. From these close passes, its suite of cameras and spectrometers will map the moons in unprecedented detail, analyzing their surface composition, density, and internal structure. This initial survey is critical, for it will inform the mission's riskiest and most important phase, the landing on Phobos. This moon presents a unique challenge. It is small, only about 17 miles across, and has such weak gravity that an astronaut could throw a baseball into orbit. Landing there is less about a controlled descent and more about a gentle, precise rendezvous. The MMX spacecraft will carefully lower itself to the surface, using thrusters to counteract its own minuscule weight. Once in contact, it will deploy a sampling mechanism to collect at least 10 grams of material from the regolith, the dusty soil that blankets Phobos. This sample will then be sealed inside a sturdy return capsule for the long journey back to Earth. But why go to all this trouble for a handful of dust from a tiny moon? The answer lies in a fundamental question that has divided planetary scientists for generations. Where did Phobos and Deimos come from? there are two leading theories, and each tells a completely different story about the history of Mars itself. The first theory suggests these moons are captured asteroids. In the early solar system, countless small, rocky bodies wandered between the planets. It is possible that a pair of these primitive asteroids strayed too close to Mars and were snared by its gravity, settling into their current orbits. If this is true, then Phobos and Deimos are not native to Mars at all, but ancient visitors from the asteroid belt. They would be time capsules preserving the original building blocks of the solar system, material that has remained unchanged for over 4 billion years. Studying their composition would give us a pristine sample of the ingredients that came together to form the rocky planets. The second, more dramatic theory proposes that these moons are the shattered remnants of a cataclysm. Early in Martian history, a colossal impact, perhaps by an object the size of a small planet, could have blasted a huge cloud of debris into orbit around Mars. Over time, that debris coalesced to form the two moons we see today. If this is true, then Phobos and Deimos are made of Martian crust mixed with material from the impacting body. A returned sample would not just be moon dust, it would be a piece of Mars itself from an era so ancient that no rock on the planet's current surface survives from that time. It would contain a record of the impact that shaped the young Mars, and possibly even clues about the planet's early climate and potential for life. The MMX sample is the key to deciding between these two histories. In Earth's advanced laboratories, scientists can perform analyses far beyond the capability of any instrument on a spacecraft. They can date the material, identify its exact mineralogy, and compare its chemical fingerprints to both known asteroid types and our limited collection of Martian meteorites. The mission also carries a tiny, innovative sidekick, a rover provided by the French and German space agencies. This small, agile robot will be deployed from the MMX mothership onto the surface of Phobos. It will traverse the strange, low-gravity terrain, providing close-up images and ground truth measurements that will help scientists understand the physical properties of the regolith and select the very best sampling site. By returning a physical piece of either a captured asteroid or a piece of primordial Mars, MMX will do more than just solve a riddle about two small moons. It will write a definitive chapter in the biography of the entire Martian system, telling us whether its satellites are adopted orphans or the children of a planetary-scale trauma. The silent moons of Mars hold stories of ancient chaos, but on our own moon, a robotic prospector is preparing for a far more practical quest. NASA VIPER rover, the Volatiles Investigating Polar Exploration rover, is a mobile laboratory built for one purpose: to find the water. Its destination is the permanently shadowed regions of the lunar South Pole, the very same enigmatic terrain targeted by the Artemis astronauts. But before humans take their historic step, VIPER must go first, acting as a scout to map the location, concentration, and form of the water ice hidden in the darkness. This is not a mission of mere discovery, it is a mission of economic geology, determining the value of the moon's most precious resource. The rover itself is a rugged, solar and battery-powered vehicle about the size of a golf cart, engineered to survive the extreme temperature swings and low-angle sunlight of the polar region. Its most critical feature is a combination of tools never before deployed on another world. At its heart is a 1-meter drill, capable of penetrating the lunar soil to extract samples from beneath the surface. This is vital because any water ice exposed directly to the vacuum of space would quickly sublimate away. It must be buried to survive. As the drill brings up soil from different depths, a suite of 3 spectrometers will immediately analyze it. One instrument, called NIRVS, will measure the presence of water and other volatile molecules by analyzing how the soil reflects near-infrared light. Another, the MSOLO, will heat the samples in a tiny oven, vaporizing any ices and measuring the specific gases released to identify their chemical fingerprints. The third, NSS, will use neutron spectroscopy to detect hydrogen signatures from up to a meter below the surface, acting as a long-range water detector to guide the rover to the most promising drill sites. VIPER's mission is a 100-day traverse across this shadowy landscape. It will drive from sun-lit ridges into the cold traps of craters that have not seen sunlight for billions of years, constantly drilling, sampling, and analyzing. The goal is to create a resource map, a detailed chart showing exactly where the water is, how much of it exists, and how it is mixed with the soil. Is it in pure sheets of ice just below the surface, or is it finely dispersed, frozen into the grains of regolith like microscopic frost? The answer dictates everything about our future there. If the ice is abundant and accessible, it becomes the cornerstone of a sustainable lunar economy. Water can be split into oxygen for astronauts to breathe and hydrogen for rocket fuel. This means a lunar base could, in principle, refuel spacecraft heading to Mars, turning the Moon into a strategic interplanetary waypoint. The water itself is also a shield, a resource that can be used for radiation protection or simply for sustaining a crew. VIPER's maps will directly inform where NASA and its partners choose to establish the first permanent outpost. They will tell engineers how to design the mining equipment and processing plants needed to harvest this off-world treasure. This small, diligent rover is therefore the critical pathfinder, transforming the promise of lunar water from a scientific hypothesis into a practical blueprint for humanity's first enduring foothold on another world. While VIPER maps the frozen water on our moon, another mission prepares to chase a different kind of ice, one that has never felt the sun's warmth. The Comet Interceptor is a patient hunter, a spacecraft with no predetermined target. Its mission is to lie in wait, parked at a gravitationally stable point 1 million miles sunward of Earth, until astronomers spot the perfect prey, a pristine comet making its first ever journey into the inner solar system. Most comets we have visited, like the famous Halley's Comet, are regular visitors. Each time they swing close to the sun, its heat boils away their volatile ices, altering their surface and erasing their original chemistry. But a comet from the distant Oort cloud, a vast spherical shell of icy debris at the solar system's edge, might take millions of years to complete a single orbit. If one is nudged inward for the very first time, it is a time capsule, an untouched relic from the dawn of our planetary system 4.6 billion years ago. The Comet Interceptor will be our first chance to meet such a virgin world. The mission is a collaboration between the European Space Agency and JAXA, and its design is as clever as its goal. It is not one spacecraft but 3. A main mothership will carry 2 smaller probes, each about the size of a suitcase. When a suitable target is identified, the combined craft will race to intercept it. Then, just days before the encounter, the mothership will release its 2 companions. All 3 will then fly past the comet's nucleus simultaneously, but from different angles and distances. Imagine 3 photographers circling a mysterious statue, each snapping pictures from a unique vantage point at the exact same moment. This multi-perspective approach is revolutionary. One probe might take a close-up shot of the comet's dark surface, while another analyzes the composition of the gas and dust jetting from its sun-warmed side. The mothership, staying farther back, captures the global structure of the comet's vast coma and tail. Together, they will create a 3-dimensional, real-time portrait of a world waking up from a billion-year deep freeze. The scientific payoff is the chance to study materials that have been in deep storage since the planets formed. We could learn the exact mixture of ices and organic compounds that were delivered to the young Earth, possibly seeding our oceans with water and our chemistry with the building blocks of life. But the mission holds an even more thrilling possibility. The Comet Interceptor could be retargeted for an interstellar object. Since the baffling visit of Oumuamua in 2017, we have known that voyagers from other star systems occasionally pass through our neighborhood. If another is detected on an approach trajectory, the spacecraft could be redirected to chase it down. Sampling or even imaging an object born around another star would be a landmark achievement. We could directly analyze the composition of another planetary system, comparing its fundamental ingredients to our own. Is the chemistry of planet formation universal, or does every star forge its own unique blend of materials? The Comet Interceptor is a mission of pure potential, a sentinel poised to greet a stranger from the deep, whether it is a pristine messenger from our own past or a visitor from a star we have never seen. The search for a second Earth demands a telescope built not for general discovery, but for a single, breathtaking purpose. NASA is already planning the successor to the James Webb Space Telescope, a revolutionary observatory known as the Habitable Worlds Observatory. This is not just another instrument, it is a machine engineered for a historic first, to take a direct photograph of a pale blue dot orbiting another star and to analyze the chemistry of its air for signs of life. Imagine looking at a star and seeing not just a point of light, but a tiny, distinct speck glowing beside it, a world. That is the goal. The challenge is immense because a planet like Earth is incredibly faint and sits vanishingly close to the overwhelming glare of its host star. It is like trying to see a firefly hovering next to a brilliant lighthouse from thousands of miles away. To solve this, the Habitable Worlds Observatory will employ a piece of technology that feels like cosmic magic, either an internal coronagraph or an external starshade. A coronagraph is an intricate mask inside the telescope itself, designed to perfectly block the starlight at the focal plane, allowing the much fainter light from the orbiting planet to become visible. Think of it as using your thumb to block the sun in the sky to see an airplane flying nearby. The engineering must be flawless, suppressing the star's light by a factor of 10 billion. The alternative is even more astonishing, a separate spacecraft flying tens of thousands of miles in front of the telescope, unfolding a giant, sunflower-shaped shade to cast a perfect shadow, blocking the starlight before it even enters the telescope's optics. This starshade would allow for even crisper images of the planet. Once the glare is suppressed, the observatory's powerful spectrometers will go to work on that faint speck of planetary light. It will break that light into a spectrum, reading the chemical barcode of the alien atmosphere. Scientists will hunt for the telltale combinations of gases that shout biology. On Earth, our atmosphere is a chemical disequilibrium maintained by life, with abundant oxygen from plants and traces of methane from microbes and other sources. Finding both oxygen and methane together in an exoplanet's air would be a powerful, though not definitive, biosignature. The telescope could also look for the green blush of vegetation or other gases like nitrous oxide that might be produced by living processes. The Habitable Worlds Observatory represents the culmination of decades of exoplanet science. Missions like PLATO will provide the target list, telling us which stars host rocky worlds in the habitable zone. The James Webb Space Telescope is learning how to analyze exoplanet atmospheres, though mostly for larger, hotter worlds. This new flagship will take that capability and focus it with laser precision on the most Earth-like candidates, moving us from statistical probability to direct interrogation. This is the mission that could provide the first credible evidence that we are not alone, that the cosmic recipe for life has been followed elsewhere. It transforms the search from inference to observation, promising not just data, but a picture, a chemical signature, and perhaps an answer. The dream of a lunar economy requires more than government plans. It needs the relentless drive of private industry. Enter Blue Origin's Blue Moon Lander, a stark symbol of how the rules of space exploration are being rewritten. This is not a spacecraft built solely for national prestige, but a versatile workhorse designed to turn the moon into a destination for business and science. Its development marks a pivotal shift where NASA acts as an anchor customer, buying services from commercial companies rather than owning every piece of hardware itself. This model, pioneered with cargo deliveries to the International Space Station, is now extending to the lunar surface, unleashing a new wave of innovation and competition. The Blue Moon lander itself is a study in pragmatic ambition. Conceived as a large multi-purpose vehicle, its initial design is for unmanned cargo missions. It stands on a broad, sturdy base, powered by efficient B-7 engines that burn liquid hydrogen and oxygen, the same propellants that could one day be sourced from lunar ice. Its most striking feature is a massive payload deck, capable of delivering several metric tons of equipment, habitats, or rovers to the Moon's surface in a single trip. This capacity is a game-changer, allowing for the pre-positioning of critical infrastructure before astronauts ever arrive. Imagine a single Blue Moon mission landing a fully stocked habitat, a power station, and a scientific laboratory at a future Artemis base camp all at once. But the vision extends far beyond cargo. A human-rated variant is already in development, designed to ferry astronauts from the lunar gateway down to the South Pole and back. This creates a fascinating dynamic, a competitive landscape for lunar access. While NASA develops its own human landing system, the existence of a commercial alternative like Blue Moon ensures redundancy, drives down costs through competition, and accelerates the overall pace of development. The implications of this commercial surge are profound. For the first time, a private company is building the infrastructure for a sustained lunar presence, not just a one-off mission. Blue Origin talks openly of a future where the Blue Moon lander operates like a scheduled freight service, enabling universities, research consortia, and even other companies to book payload space. A mining startup could send a prototype excavator. A pharmaceutical company could fly an experiment requiring lunar gravity. This competitive market does more than just share costs. It democratizes access and multiplies the reasons for going. When profit becomes a motive alongside discovery, the pace of innovation quickens dramatically. The lessons learned in building reliable, reusable lunar landers will inevitably filter into technologies for other worlds. The rise of companies like Blue Origin transforms the Moon from a government-owned outpost into a frontier with many open doors, where the next giant leap may be funded by a venture capitalist as easily as by a taxpayer. The dream of a lunar outpost, however ambitious, is merely a stepping stone in a far grander vision unfolding in Texas. SpaceX's Starship represents a fundamental break from every spacecraft that has come before it, a machine engineered not for a single mission, but for the birth of a new branch of civilization. This is not a capsule or a lander, it is a fully reusable interplanetary transport system, a skyscraper of stainless steel designed to carry the weight of a species' future. Its most staggering feature is its sheer scale. When fully stacked with its super-heavy booster, Starship stands nearly 400 feet tall, a leviathan capable of lofting over 100 metric tons of cargo to the surface of the Moon or Mars. That payload capacity changes everything. Instead of sending a single, cramped habitat module, Starship could deliver an entire prefabricated laboratory, a greenhouse, or a power station in one flight. But its true genius lies in reusability. The entire system, both the massive booster and the Starship spacecraft itself, is designed to land back on Earth, be refueled, and fly again, dramatically slashing the cost of access to space from billions per launch to potentially millions. This transforms spaceflight from a rare national event into a routine industrial operation. The architecture for reaching Mars hinges on a delicate cosmic ballet called orbital refueling. A single Starship launched from Earth does not carry enough propellant to reach the red planet and land, so the plan involves a fleet of tanker Starships. These tankers would launch into orbit one after another and rendezvous with a waiting Mars-bound Starship, transferring their loads of liquid methane and liquid oxygen until its tanks are full. Only then, with a fully fueled spacecraft in orbit, does the final engine burn for Mars commence. This process turns low Earth orbit into a celestial gas station, and while it requires an unprecedented number of launches and flawless orbital rendezvous, it solves the fundamental physics problem of deep space travel. The long-term vision driving this monumental engineering effort is nothing less than the establishment of a self-sustaining city on Mars. Elon Musk speaks of a future where 1 million people live on the red planet, not as visitors in isolated habitats, but as a thriving, independent civilization. This is the core of the multi-planetary species argument, a hedge against existential risk for humanity. If a catastrophe were to befall Earth, a backup on Mars ensures the light of consciousness survives. The challenges of achieving this are, of course, titanic. Mars is a frozen desert with a thin, toxic atmosphere. Establishing a self-sustaining city means mastering technologies we are only beginning to conceive. We would need to build massive, radiation-shielded habitats, likely using Martian soil itself as a protective barrier. We would have to develop closed-loop life support systems that recycle every drop of water and molecule of air with near-perfect efficiency. Most critically, we would have to learn to live off the land, a process called in situ resource utilization. This means using Martian water ice to create drinking water, breathable oxygen, and rocket propellant. It means using the carbon dioxide in the atmosphere to produce methane fuel and possibly plastics. It means using the regolith to grow food in pressurized greenhouses, using tailored bacteria to process soil, and eventually manufacturing the tools and materials needed for expansion from local resources alone. The psychological and social challenges are equally profound. A Martian colony would be isolated from Earth by a minimum communication delay of 20 minutes, creating a sense of profound disconnect. The first settlers would live in a perpetual state of risk, utterly dependent on complex machines for survival in an environment that offers no second chances. Yet this is the transformative potential of Starship. By providing a cheap, high-capacity railroad to Mars, it shifts the question from "can we get there?" to "what will we build when we arrive?" It turns a science fiction fantasy into a formidable, albeit distant, engineering project, inviting us to confront not just the mechanics of flight, but the very blueprint for a new society under an alien sky. This vision of a city on Mars is a testament to human audacity, but to understand the universe we hope to populate, we must first learn to listen to its oldest stories. The most ambitious ear ever constructed is now rising from the deserts of South Africa and the plains of Western Australia, a machine designed to hear the faintest whispers from the edge of time. This is the Square Kilometre Array Observatory, or SKA, and while its components are rooted to the Earth, its purpose is truly cosmic. It will not be a single dish, but a sprawling web of technology, eventually comprising thousands of individual radio antennas spread across 2 continents. In South Africa, mid-frequency dishes will dot the arid landscape, while in Australia, a forest of low-frequency antennas will stand like silent, metallic trees. Together, they will function as one colossal instrument with a total collecting area of, as the name suggests, over 1 square kilometre. This gives it a sensitivity that dwarfs any existing radio telescope, allowing it to detect the faintest signals from the deepest reaches of space and time. Its first great mission is to witness the universe's first sunrise, a period called the Cosmic Dawn. For hundreds of millions of years after the Big Bang, the universe was dark, filled with a fog of neutral hydrogen gas. Then the first stars and galaxies ignited. Their intense ultraviolet radiation began to strip electrons from those hydrogen atoms, a process called reionization, gradually clearing the fog and making the universe transparent. The SK is designed to detect the faint radio hum emitted by that primordial hydrogen itself, a signal that has been traveling for over 13 billion years and is now stretched into long radio waves by the expansion of the universe. By mapping this signal, the telescope will create a 3-dimensional movie of the universe's first chapters, watching as the first great structures flicker to life and begin to sculpt the cosmos. Beyond this ancient light, the array will map an invisible force that weaves through the galaxy: cosmic magnetism. Magnetic fields are everywhere in space, threading through galaxies, guiding the collapse of gas clouds into stars and accelerating particles to near light speed. Yet we know surprisingly little about their origin and large-scale structure. The SKA, with its exquisite sensitivity, will detect the subtle polarization of radio waves from billions of distant galaxies, allowing astronomers to trace these magnetic fields across the vast cosmic web for the first time. It will show us how magnetism helped shape the universe we see today. The observatory will also serve as a fundamental physics laboratory, testing the very laws of the cosmos. By timing the pulses from distant, ultra-regular neutron stars called pulsars with phenomenal precision, the SKA will search for the background rumble of gravitational waves from merging supermassive black holes, complementing space-based detectors like LISA. It will use these celestial clocks to test Einstein's theory of general relativity under the most extreme conditions, watching for any tiny deviation that might hint at new physics. And then, of course, there is the question that stirs the imagination of everyone who looks up. The SKA will conduct the most comprehensive search for technosignatures ever attempted, listening for artificial radio signals that could indicate the presence of intelligence elsewhere in the galaxy. Its sheer power means it could detect a signal akin to our own civilian radar transmissions from a star tens of light years away, or find unintentional leakage from a civilization much more advanced than our own. It will listen across millions of star systems, turning a hopeful speculation into a systematic scientific investigation. This vast electronic ear, tuned to the longest waves of the electromagnetic spectrum, will hear a universe invisible to optical telescopes. It will listen to the birth of the first stars, trace the ghostly lines of magnetic force, interrogate the fabric of spacetime, and perhaps, just perhaps, catch a signal that changes our understanding of our place in the cosmos forever. But to truly touch the galaxy, we must first step outside our own protective bubble. The final mission on this list is perhaps the most profound, a concept that looks beyond the orbits of planets, beyond the influence of our sun, into the dark river of the galaxy itself. NASA Interstellar Probe is a vision for a spacecraft that would do what only two human-made objects have ever done by accident: leave our solar system entirely, but this time with purpose. The Voyager probes, now drifting in the void, were designed to explore the outer planets, their escape into interstellar space a fortunate bonus. The Interstellar Probe would be built from the ground up for one goal: to journey into the unknown ocean beyond the sun's reach, carrying instruments to study the pristine galaxy for the first time. Its target distance is staggering: 1,000 astronomical units from the sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. The probe would aim for a point 1,000 times farther out, a journey that would take it well beyond the heliosphere, the vast magnetic bubble blown by the solar wind that encapsulates our entire planetary system. This bubble is our celestial home, shielding us from the harsh interstellar medium. The Interstellar Probe would be the first dedicated mission to turn around and look back at that bubble to map its full global shape. Is it a perfect sphere or a teardrop stretched by the galactic wind? We have only glimpsed it from the inside, like a fish trying to understand the pond from the murky center. By flying perpendicular to the Voyager's paths, this probe would give us a three-dimensional portrait of our solar home, a self-portrait of humanity's place in the cosmic flow. Once beyond this protective shield, the spacecraft would immerse itself in the true interstellar medium. This is the thin soup of gas, dust, and cosmic rays that fills the space between the stars. From within this pristine environment, its sensors could measure the exact composition and density of this galactic material, free from the contamination of the solar wind. It could directly sample the building blocks from which new stars and planets are born, giving us a pure reading of the galaxy's chemistry. perhaps most critically, the probe would become a direct monitor for cosmic rays from deep space. These high-energy particles, accelerated by distant supernova and black holes, constantly bombard our heliosphere. By measuring their flux and energy from outside our protective bubble, scientists could finally understand the true radiation environment of the galaxy, essential knowledge for any future dream of long-duration crewed missions beyond our solar system. The engineering challenge is, of course, monumental. To reach 1,000 astronomical units within a reasonable human lifespan, perhaps 50 years, the spacecraft would need unprecedented speed. This would likely require a gravity-assist slingshot around Jupiter, followed by a close, scorching pass by the Sun itself, using our star's gravity as a catapult to achieve velocities that could approach 7 astronomical units per year. The probe would need to be incredibly robust to survive that solar encounter, and then operate autonomously in the deepening cold and dark for decades, its nuclear power source slowly fading, its signal back to Earth growing ever fainter. This is a mission for the centuries, a gift from one generation of humanity to those that follow. It carries no immediate practical return, no resource to mine, no world to claim. Its value is pure knowledge, a testament to our need to see what lies beyond the next hill, even when that hill is light years away. The Interstellar Probe would be our first deliberate step into the galactic tide, a message in a bottle cast into the ocean of stars, not to find others, but to finally understand the sea in which we all sail. 25 separate missions, each a thread in a tapestry of discovery being woven across the solar system and beyond. From the dusty plains of the Moon to the hidden oceans of Europa, from the scorching winds of Venus to the silent gravity waves between galaxies, humanity is not pursuing a single goal but a symphony of questions. We are returning to worlds we barely know to build permanent homes. We are sending robots to fetch pieces of other planets and daring to chase comets from the edge of darkness. We are building telescopes that can see the first light of creation and hear the hum of colliding black holes. We are designing ships to carry cities and probes to sail on beams of light. Collectively, this is more than a schedule of launches. It is the opening of a new golden age, one defined not by a competition between nations, but by a shared, species-wide curiosity. The fundamental puzzles that have haunted us for millennia are now within our reach. Where did we come from? Are we alone? What is our destiny among the stars? These missions are our way of seeking answers, of turning wonder into knowledge. Every signal from a distant telescope, every image from a far-off lander, every sample returned from an alien world is a piece of a grander story being written in real time. The discoveries that could change everything are not relics of a past era. They are unfolding in front of us. The data streams are live, the rockets are on the pads, the engineers are at their consoles. This is our moment to witness, to follow along, and to remember that the greatest adventure is the one happening right now. Stay curious, the universe is waiting.